Hello everyone, good morning. Okay, for today's discussion, we shall be able to discuss about metals. So metals are not new to us guys because we can see this anywhere and everywhere. Okay, so the learning outcomes or objectives to this lesson is that at the end of the lesson, the learners will be able to understand about metals, identify the different types of metals, and acknowledge some application of metals. Introduction. Throughout history and the advancements of civilization, the discovery, development, and application of metals has driven the way that people live and societies have been originally shaped. Historians use the intrinsic link of industrial development and the metals discovered and prevalent at that time to describe certain periods of significant social and technological advancements, such as the Stone Age, Bronze Age, and Iron Age. Okay, so here are the pictures of the different ages. First picture, we have the Stone Age, as you can see the picture class. Second, we have the Bronze Age. Third, we have the Iron Age. Okay. Since man first discovered copper around 9000 BC or before Christ, naturally occurring, relatively pure metal, native to many countries. The study and knowledge of metallurgy has been fundamental to the way humans have lived, stemming from a very basic curiosity as to how this new material could be used and its behavior in various situations and under a variety of conditions. Metallurgy has developed from an art to a science. So, the history of metals is that the development of civilization has relied heavily on the discovery of metals. Prehistoric man used metals to build tools and weapons, and as our knowledge of metallurgy has developed, metals have played an essential role in the advancements of agriculture, transport and arts and crafts, forging and path to today's modern society. There are currently 86 known metals, but before the 19th century, only 24 had been discovered, and of these 24 metals, 12 were discovered in the 18th century. The metals of antiquity were the metals upon which civilization was based. First, we have gold. So, on 6000 or 600 BC, Stone Age, man learned to fashion gold into jewelry. The popularity of gold is largely due to its scarcity, value, and mankind's fascination with the metal. Second, we have copper. On 4200 BC, the use of copper in antiquity is of more significance than gold, as the first tools, implements, and weapons were made from copper. Third, we have silver. On 4000 BC, silver had been widely used throughout time as a basis for monetary systems and played central roles in the currencies of the Roman and Chinese empires. Fourth, we have lead. On 3500 BC, it is believed that lead smelting began at least 9,000 years ago. And the oldest known artifact of lead is a statuette found at the temple of Osiris on the site of Abydos, dated circa 3800 BC. Fifth, we have tin. On 1750 BC, first smelted in combination with copper around 3500 BC to produce bronze. The oldest artifacts that date from around 2000 BC. 6. We have iron smelted. On 1500 BC, the discovery of smelting around 3000 BC led to the start of the Iron Age around 1200 BC and the prominent use of iron for tools and weapons. 7th, we have the mercury. On 750 BC, known to ancient Chinese and Indians before 2000 BC, and found in Egyptian tombs during or tombs dating from 1550 or 500 BC. Sorry. Okay, so here are the chemical elements. First, we have on 1735, we have cobalt. 1751, nickel. 1774, manganese. 1781, molybdenum. 1782, tellurium. 1783, tungsten. 1789, uranium. 1789, zirconium. 1791, titanium. 1791, yttrium. 1797, beryllium. 1797, chromium. 1801, niobium. 1802, tantalum. 1803, iridium, palladium, and rhodium. On 1807, potassium and sodium. 1808, boron, barium, calcium, magnesium, and strontium. 1814, cerium. 1817, lithium, cadmium, selenium. 1823, silicon. 1827, aluminum. 1828, thorium. 1830, vanadium. 1839, lanthanum. 1843, erbium and terbium. 1844, ruthenium. 1860, caesium, rubidium. 1861, thallium. 1863, indium. 1875, gallium. And we have the on 1878 and 1885, we have helium, thallium, scandium, samarium, gadolinium, praseodymium, neodymium, dysprosium. On 1886, germanium. 1898, polonium and radium. 1899, actinium. 1801, europium. 1807, latinium. 1917, protactinium. 1923, hafnium. 1924, rhenium. 1937, technetium. 1939, francium. 1945, promethium. From 1940 to 1961, we have transuranium elements. Neptunium, plutonium, chromium, americium, berkelium, californium, einsteinium, formium, mendelevium, nobelium, lawrencium. So that was all the chemical elements of metals. Okay, so let's proceed. Okay, class, are you there? So, class, I have here a question about what is metals. So, who have here the idea about what is metals? Anyone from the group? Okay, so if none, then let's proceed. So, metals are opaque, lustrous elements that are good conductors of heat and electricity. Most metals are malleable and ductile and are, in general, denser than the other elemental substances. Okay, so here are the pictures of things that made up of metals. So without metals, we cannot see in our naked eye these things. Okay, so first picture we have the broker. So this is broker class. Broker. Second, we have the recycling metals. Third, we have the metal wood salvage. So precious metals and stones. This metals class, we call this gold bar or gold. Last, we have the native metal. So native metal is any metal that is found pure in its metallic form in nature. Over geological time scales, very few metals can resist naturally or natural weathering, weathering processes like oxidation. So mainly, the less reaction metals such as gold and platinum are found as native metals. Okay, class. So, before we moving on to the different types of metals, let us watch first the short video about the application of metals.
What are metals? Metals are all around us, but did you ever take time to really understand what makes a metal and what makes metals different from other materials? Here's a dictionary definition of what metals are. Any of various opaque, fusible, ductile, and typically lustrous substance that are good conductors of electricity and heat, form cations by loss of electrons, and yield basic oxides and hydroxides, especially one that is a chemical element as distinguished from an alloy. Now let's start near the end of this definition and work backward. A chemical element. A good place to start looking at metals is on the periodic table of the elements. Just by glancing around this table, you may recognize some of the more common metals. Here's iron, copper, aluminum, silver, and gold. But what you may not have seen before is that most of the elements on this table are actually metals. Here, I'll remove the elements that are not metals from the table. Okay, now you can see that there are many metals on the periodic table. You'll also notice that the metals are all grouped together on the left side of the table. This is because of how the atoms that make up the metals are put together. If we take a closer look at this, we can get an even better understanding of what makes a metal and why they have the properties they do. Now, you're probably familiar with the fact that inside each atom there's a nucleus. Inside the nucleus there are protons and neutrons. Protons have a positive charge and neutrons have no charge. It's the number of protons in the nucleus that determines what the element is. For instance, this atom has 3 protons in its nucleus. That means that this element is lithium. The number of neutrons in the nucleus of an atom is usually pretty close to the number of protons in an atom, but it doesn't have to be. The number of neutrons in an atom determines the isotope of a particular element. Lithium has 3 or 4 neutrons in its nucleus. We call these the lithium-6 and lithium-7 isotopes. You see, the number comes from adding the number of protons and neutrons in the nucleus. Now, if we look at this simplified version of an atom, we can see that there are electrons flying around the nucleus. Remember that electrons have a negative charge, and in a neutral atom, the number of electrons equals the number of protons. But it's possible to have a different number of protons and electrons. When the number of protons and electrons is not matched, the atom becomes electrically charged, and we refer to it as an ion. If an ion has more electrons than protons, it's negatively charged and it's called an anion. If it has more protons than electrons, it's positively charged and becomes a cation. We can see from our definition that metals tend to give up electrons and become cations. Now let's look at the shells around the nucleus that the electrons swim around in. There are rules about how many electrons can go into each shell. We're going to simplify these rules just a little. The inside shell can hold 2 electrons, and for the most part, the outside shell can hold up to 8. If there are shells in between, they can hold different numbers, but we're mostly interested in the outside shells right now. An important fact in chemistry is that atoms really like to have 8 electrons in their outer shell if they can. Let's build a few atoms and see how the periodic table is arranged according to this pattern. What do we need to build our first atom? We need a proton. Here we go, 1 proton. That means we're dealing with hydrogen. We can give it a neutron or even 2 neutrons if we like. These are the isotopes of hydrogen, called protium, deuterium, and tritium. Now, to make it electrically neutral, we can give it an electron. So here we only have 1 shell. It's the inside shell, so remember it can only hold up to 2 electrons. Let's add a proton and see what happens. With 2 protons, we don't have hydrogen anymore. We now have helium. Helium is a well-balanced element. If we give it 2 neutrons and 2 electrons, it will be quite content not to react with any other element. Its outer shell has 2 electrons to fill it up, and its charge is balanced. Since the first shell is filled, the first row of the periodic table is filled. Now, things get interesting when we add another proton to create lithium. For lithium to be electrically balanced, it needs 3 electrons. But if we try to give lithium 3 electrons, they won't all fit in the 2-electron inner shell, and the outside shell begins filling up. This shell can hold up to 8 electrons, but there's just 1 electron sitting there. This makes lithium feel a little self-conscious. Atoms want to look well-balanced on the outside, so what lithium would like to do is to get rid of that single electron in its outer shell. Sometimes an atom would rather carry a charge than to have 1 electron in their outer shell. The elements in this whole column all work this way. They are called alkali metals. Alkali metals react easily because this single outer electron is very unstable. Alkali metals are famous for their violent reactions with water. Just look them up on YouTube and you'll see what I mean. Now, let's add more protons and electrons to see the shells fill up. Here's beryllium, carbon, nitrogen, oxygen, fluorine, and finally neon. Do you see how we've filled up all the available spaces in the shells? Neon, like helium, has a completely filled outer shell. In fact, this is true of all the elements in this column. The elements here are called the noble gases. Because their outer shell is full, they tend not to react with anything. Now, this is a useful property. For example, argon and helium are often used as shielding gases to prevent reactions from taking place during welding. As we keep adding protons and filling shells with electrons, we can see that a pattern emerges. As the shells fill up, the properties of the elements seem to repeat. Here we're back to the first column, the alkali metals. In the second column, here, the outer shell has 2 electrons. The metals in this column are called the alkaline earth metals, and while they don't react as violently as the alkali metals, they do react easily. And that's because they have 2 electrons in their outer shell. They would rather lose these electrons than be electrically balanced. In fact, losing or giving away electrons is what metals do so well. As we move across the table, we pass through the transition metals. It's easy to find familiar metals in this group of elements. Here is titanium, chromium, iron, nickel, and copper. Look at what happens as we add protons to move across the table. See how the in-between shells are beginning to fill up? See how the inside shell still has 2 electrons, but the outside shell almost always has less than 8. Now you can see that metals tend to have low numbers of electrons in their outer shells. Now this means they can easily give up or donate those electrons. So that's 3 metal groups so far: the alkali metals, alkaline earth metals, and the transition metals. Here is one more group, the post-transition metals. Now, these are sometimes called the poor metals or other metals. Here too, you'll see some familiar metals. Here's aluminum, tin, and lead. Now to contrast, let's look at some of the non-metals. The non-metals tend to be takers of electrons instead of givers of electrons like the metals are. Let's quickly look at how this makes atoms stick together to form molecules, because that will give us more insight into what metals are and why they have the properties they do. You probably remember that there are 3 different kinds of chemical bonds: ionic bonds, covalent bonds, and metallic bonds. Let's review those and then look in particular at the metallic bonds. Ionic bonds. Let's look at sodium and chlorine for a minute. See how they're at different ends of the periodic table? Sodium has one electron in its outer shell. Remember that the metals like to give up electrons, so sodium would very easily give up this electron to have a nice, neat outer shell with 8 electrons. And here is chlorine. Chlorine has 7 electrons in its outer shell. If it could just get one more electron, it would become stable, like a noble gas. So when sodium and chlorine are close to each other, and they're given just a little push of energy, the electron leaves the sodium for good and becomes part of the chlorine atom. This gives the sodium a positive charge and the chlorine a negative charge. Do you remember the name of an electrically charged atom? They're called ions, and ions of different charges attract each other. So the sodium and chlorine stay attached to each other by this newly formed ionic bond. Notice that with this arrangement, we can say these particular electrons belong to the chlorine atom and these belong to the sodium atom. Covalent bonds. Let's take a look at an element that has a half-filled outer shell. This is carbon. It has 4 electrons in a shell that could ideally hold 8. Carbon is not eager to give up electrons, and it's not likely to just pull in 4 electrons just to have its outer shell filled. What it does do nicely is work out a sort of timeshare agreement with elements like hydrogen. You see, if hydrogen and carbon are encouraged just a little, they can work out a sharing plan between themselves, a sort of custody agreement with the electrons. You see, 4 hydrogen atoms, 1 carbon atom can share electrons with each other. Hydrogen can have 2 electrons in its outer shell and it will be stable. Carbon can have 8 to be stable. They can share electrons to make this happen. This electron is shared between this hydrogen atom and this carbon atom. If carbon can do this with enough other atoms, it can look like it has 8 electrons in its outer or valence shell. This sharing type of bond is what's called a covalent bond, and you can see it being used in all kinds of molecules. For example, this neat paraffin molecule, metallic bonds. Okay, now, when metals are around other metals, a really neat thing happens. The metal atoms all share their outer electrons freely. Since they hold their outer electrons very loosely, the electrons are free to move around this group of metal atoms. The atoms are positively charged ions, or cations, because they've all given up their outer electrons. This field or sea of electrons attracts the metal cations and holds them together because of their opposite charges. This is a metallic bond. It's a strong bond that only occurs to hold metals to other metals. In fact, it's this unique bonding phenomenon that explains a lot of the properties of metals. When light strikes a metal, it hits the freely mobile electrons and bounces right off. This explains why light won't go through the metal. And in fact, this bouncing back of light explains the shininess or lustrous property of metals. Metals are also ductile, malleable. This means they can be bent or hammered without. The metallic bonds allow the atoms that make up the material to slide past each other and remain bonded. Ionic bonds and covalent bonds do not allow this type of behavior. It's probably easy to see at this point why metals are such good conductors of electricity. Electrical current is the flowing, the moving of electrons. The valence electrons in metals are free-flowing. They're not attached to any atom in particular. This free movement also allows heat to be conducted through the metal. When you look at the periodic table, you might notice that some metals seem to be missing. For instance, there's no steel or brass on the table. That's because those metals are not pure elemental metals. They are what is known as alloys or metals. Alloys are metals that are combined with other elements, either metals or not. For example, brass is an alloy. Brass is a combination of copper and zinc. We'll deal with oxidation in a later video, but based on what you know about metals and their electrons, you'll probably have a pretty good head start on understanding what happens during oxidation. Just look up a video on oxidation and reduction reactions. I'll link to one in the description below. So, in review, metals are elements on the left side of the periodic table. They tend to donate electrons from their outer shells. Metals form metallic bonds with each other And this special type of bond is responsible for many of the properties that characterize metals. Alloys are not pure elemental metals, they're a combination of a metal with other elements.
Okay, so that videos shows about what metals are all about.
Hello everyone, I am Quisel. I am going to discuss to you about the different types of metals. So, the steel. It is an alloy made of iron with typically a few tenths of a percent of carbon to improve its strength and fracture resistance compared to other forms of iron. Many other elements may be present or added. Stainless steels that are corrosion and oxidation resistant need typically an additional 11% chromium. Carbon steel is a steel with carbon content from about 0.005 up and to 2.1% by weight. So alloy steel is steel that is alloyed with a variety of elements in total amounts between 1.0% and 50% by weight to improve its mechanical properties. And the stainless steel is a group of ferrous alloys that contain a minimum of approximately 11% chromium, a composition that prevents the iron from rusting and also provides heat-resistant properties. So iron or wrought or cast. So wrought iron is iron that has been heated and then worked with tools. So painitan siya. Then ang cast iron is iron that has been melted. So ilanay, poured into a mold and allowed to solidify. Aluminum is a silver-colored low-density metal used in a variety of commercial applications. So copper is a soft, malleable, and ductile metal with very high thermal and electrical conductivity. A freshly exposed surface of pure copper has a pinkish-orange color. So yung color is pinkish-orange color. Nasa picture, oh. May makuhaan siya nga. So the brass is an alloy of copper and zinc in proportions which can be varied to achieve varying mechanical, electrical, and chemical properties. So let's proceed to bronze. It is an alloy consisting primarily of copper, commonly with about 12 to 12.5% tin, and often with the addition of other metals such as aluminum, manganese, nickel, or zinc, and sometimes nonmetals or metalloids such as arsenic, phosphorus, or silicon. So the zinc, it is a chemical element with the symbol Zn. So yung symbol is Zn. An atomic number, it has an atomic number of 30. It is a slightly brittle metal at room temperature and has a silvery grayish appearance with oxidation is removed. So the titanium is a chemical element with a symbol Ti and atomic number of 22. Its atomic weight is 47.867. Measured in Daltons, it is a lustrous transition metal with a silver color, low density and high strength, resistant to corrosion in seawater, aqua regia, and chlorine. So the tungsten, or the other term for tungsten is wolfram, is a chemical element with a symbol of W and atomic number of 74. Tungsten is a rare metal found naturally on Earth, almost exclusively as compounds with other elements. It was identified as a new element in 1781 and first isolated as a metal in 1783. So the adamantium is a fictional metal alloy appearing in American comic books, published by Marvel Comics. So naisalidaan ni. It is best known as the substance bonded with the character Wolverine's skeleton and claws. So katong salida ni Wolverine katong sa iyang kamot. Ano siya? Nickel is a chemical element with a symbol Ni and atomic number of 28. It is a silvery white, lustrous metal with a slight golden tint. Nickel belongs to the transition metals and is hard and ductile. So cobalt is a chemical element with the symbol Co and atomic number of 27. Like nickel, cobalt is found in the Earth's crust only in the chemically combined form, save for small deposits found in alloys of natural meteoric iron. The free element produced by reductive smelting is a hard, lustrous, silver-gray metal. So the tin is a chemical element with the symbol Sn and atomic number of 50. Tin is a silvery metal that characteristically has a faint yellow hue. Tin is soft enough to be cut with little force. So, lata. Dali siya maabayan kay nipis naman siya. Okay, the lead is a chemical element with a symbol Pb and atomic number of 82. It is a heavy metal that is denser than most common materials. Lead is soft and malleable, and also has a relatively low melting point. When freshly cut, lead is silvery with a hint of blue. It tarnishes to a dull gray color when exposed to air. So, let's go to silicon. So, a silicon is a chemical element with a symbol Si and atomic number 14. It is a hard, brittle, crystalline solid with a blue-gray metallic luster and is a tetravalent metalloid and semiconductor. It is a member of group 14 in the periodic table. Carbon is above it. And germanium, tin, lead, the flerovium are below it. So, what are some applications of metals? So, metals are used in transportations like cars, buses, trucks, train ships, and airplanes. So, aeroscope, unmanned and manned rockets and the space shuttle. Computers and other electronic devices that require conductors. TV, these are the TV, radio, stereo, calculators, security devices, and etc. So communications also, including satellites that depend on a tough but light metal shell. So also in food processing and preservation like microwave and conventional ovens and refrigerators and freezers. So construction, nails in conventional lumber, construction and structural steel in other buildings. So biomedical applications as artificial replacement for joints and other prostheses. Electrical power production and distribution. Distribution is our boilers, turbines, generators, transformers, power lines, nuclear reactors, oil wells, and pipelines. So, in farming, tractors, combines, planters, etc. Household conveniences like oven, the dishes, and clothes washers, vacuum cleaners, blenders, pumps, lawn, mowers and trimmers, plumbing, water heaters, heating, cooling, etc. So useful kayo ang metals. So metal, any of a class of substances characterized by high electrical and thermal conductivity as well as by malleability, ductility, and high reflectivity of light. So approximately 3/4 of all non-chemical elements are metals. The most abundant varieties in Earth's crust are the aluminum, iron, calcium, sodium, potassium, and magnesium. The vast majority of metals are found in ores, or mineral-bearing substances, but a few such as copper, gold, platinum, and silver frequently occur in the free state because they do not readily react with other elements. So metals are usually crystalline solids. In most cases, they have a relatively simple crystal structure, distinguished by a close packing of atoms and a high degree of symmetry. Typically, the atoms of metals contain less than half the full complement of electrons in their outermost shell. Because of this characteristic, metals tend not to form compounds with each other. They do, however, combine more readily with nonmetals, oxygen and sulfur, which generally have more than half the maximum number of valence electrons. So metals differ widely in their chemical creativity. The most reactive include lithium, potassium, and radium, whereas those of low reactivity are gold, silver, palladium, and platinum. So, the high electrical and thermal conductivities of simple metals, these are the illustrative examples. The non-transition metals of the periodic table are best explained by reference to the free electron theory. According to this concept, the individual atoms in such metals have lost their valence electrons to the entire solid, and these free electrons that give rise to conductivity move as a group throughout the solid. In the case of the more complex metals, the transition elements, conductivities are better explained by band theory, which takes into account not only the presence of free electrons, but also their interaction with so-called electrons. So, the mechanical properties of metals such as hardness, ability to resist repeated stressing or fatigue strength, ductility, and malleability are often attributed to defects or imperfections in the crystal structure. The absence of a layer of atoms in its densely packed structure, for example, enables a metal to deform plastically and prevents it from being brittle. So these are our references, and that's all. Thank you, and I hope you learned something in our report. Thank you.